In very hot flames, some ionization may occur, making part of the fire behave like plasma. Plasma. Plasma is often referred to as the fourth state of matter, distinct from solids, liquids, and gases. It's found in stars, lightning, neon signs, and more. In summary, while fire can contain plasma under certain conditions, they are not the same. Fire is primarily a chemical reaction, while plasma is a distinct physical state characterized by ionization. In theory, a small ball of plasma could heat a large space because plasma is an extremely hot state of matter, with temperatures that can reach or exceed those found in the core of the Sun. However, in practice, the ability of a small amount of plasma to heat a large space would depend on several factors. Containment. Plasma must be contained within a magnetic field or some form of enclosure to maintain its state, as it will otherwise dissipate quickly into the surrounding environment. Yes, plasma televisions do use actual plasma. They operate by filling tiny cells between two panels of glass with a mixture of noble gases that are then electrically charged to create plasma. This plasma emits ultraviolet light, which strikes phosphors coated on the inside of the cells, producing visible light that forms the images on the screen. However, they have been largely superseded by LCD and OLED technologies due to improvements in efficiency, cost, and the ability to produce lighter and thinner screens. Plasma displays are often credited with having high refresh rates, which can be misleading. However, this doesn't mean they display 600 individual frames per second. LCD and OLED technologies have different mechanisms for displaying images. LCDs use a backlight to illuminate pixels, while OLED pixels produce their own light. OLEDs generally have faster response times than LCDs, which can result in smoother motion on screen. However, most content doesn't exceed 120 FPS, so having a display capable of higher refresh rates doesn't necessarily translate to a better viewing experience due to content limitations. The perception of seeing things here or not here at the same time is more related to persistence of vision and the response time of the display technology rather than the refresh rate itself. Plasma's quick response time can reduce motion blur, making fast-moving content clearer, but it doesn't allow us to perceive light in a fundamentally different way than other display technologies. Matching the frame rate of a television to the frame rate of the universe is a thought-provoking concept, but it's important to clarify that the universe doesn't have a frame rate in the same way a television does. The frame rate of a TV is a measure of how many images, frames, it can display per second, which is a concept rooted in the technology of image reproduction. The universe, on the other hand, doesn't blink in and out of existence in discrete intervals like frames in a video. However, if we were to consider the smallest measurable time interval, known as the Planck time, 10⁻⁻43 seconds, it could be likened to a theoretical frame rate of the universe. This is the scale at which classical ideas about gravity and space-time cease to apply and quantum effects dominate. As for the amount of information the universe processes, this is a more abstract concept. Information in physics is often discussed in terms of entropy or the states of particles. The universe is constantly processing information at the quantum level, with particles interacting and changing states. However, quantifying this in terms of information per second isn't straightforward and is more a topic of theoretical physics and quantum computing. The idea of using the ocean as a giant eyeball or a neural network with immense computational power is a poetic and imaginative concept. While it's not literally possible to use the ocean as an eyeball or a neural network, the ocean does contain vast amounts of information and complex systems that scientists are still working to understand. In a metaphorical sense, the ocean's intricate interactions among its physical, chemical, and biological components can be likened to a vast network. For instance, the movement of water masses carries heat and nutrients across the globe, affecting weather patterns and marine life, much like how information is processed in a neural network. Moreover, advancements in technology have enabled us to harness some of this complexity. So, while we can't use the ocean as a neural network in the literal sense, we can apply neural network technology to better understand and interpret the vast data that the ocean holds, which could lead to more accurate predictions and models of oceanic and global phenomena. Your concept of using the ocean as a vast sensor to gather data from the universe is quite imaginative. In a way, the ocean does act as a natural sensor, collecting information through its interactions with the environment. Scientists use various technologies to tap into this data for research and monitoring purposes. For instance, the World Ocean Database is a collection of ocean profile data that serves as a powerful tool for oceanographic, climatic, and environmental research. Additionally, NOAA uses instruments like drifters, buoys, and Argo floats to monitor the global ocean, collecting critical data on temperature, salinity, and other factors. These data collection methods are akin to your idea of using buoys connected to a digital apparatus. They help us understand the ocean's role in climate change, marine ecosystems, and more. While we can't literally use the ocean as an eye to see photons, we can use it to detect and measure various physical and chemical properties, which in turn tell us a lot about the health of our planet and the universe's influence on it. The concept of using a large body of water as a detector for cosmological events is quite intriguing. In fact, water is used in some types of astrophysical observatories. For example, neutrino observatories often use large volumes of water or ice to detect these elusive particles as they interact with atoms in the water. When a neutrino interacts with the nucleus of an atom, it can create a charged particle that moves faster than the speed of light in water, emitting a cone of light known as Cherenkov radiation, which can be detected. Cosmic rays, which are high-energy particles from space, also interact with Earth's atmosphere and can produce showers of secondary particles, some of which reach the surface and can be detected in water. Researchers have used water to study the interactions of cosmic rays and to measure their energy loss through processes like Bremsstrahlung. On a quantum scale, the interactions of particles with water are indeed influenced by events in the universe, but these are typically on a scale that is not influenced by every tiny event. The interactions are probabilistic and governed by the laws of quantum mechanics. Detecting and measuring these interactions requires highly sensitive equipment and often involves looking for very specific types of events or particles. While it's true that water is more easily measured and manipulated than land, the idea of using water to detect every tiny event in the universe is beyond our current technological capabilities. The universe is vast, and the interactions that occur are numerous and often require specialized conditions to be observed. However, the principle of using water as a medium to detect and study cosmological and quantum phenomena is a valid and active area of scientific research. The idea of using swimming pools filled with specific chemicals and nanoparticles to detect various cosmic events and gather comprehensive data about the universe is a creative and futuristic concept. While we currently do not have the technology to create such a universal detection system, the principle behind your idea is somewhat reflected in the way certain scientific instruments work today. For instance, neutrino observatories use large volumes of water or ice to detect neutrinos, which are nearly massless particles that rarely interact with matter. When neutrinos do interact with the nuclei in water, they can produce detectable light signals. Similarly, nanoparticles have been studied for their potential to enhance the critical heat flux in pool boiling, which could be related to detecting energy transfer in various applications. However, the practical implementation of using swimming pools as universal sensors is highly complex. It would require a deep understanding of the interactions between various chemicals, nanoparticles, and cosmic phenomena. Moreover, the safety, environmental impact, and feasibility of deploying such pools around the world would need careful consideration. The concept of retrofitting existing electrical and lighting systems into Li-Fi light fidelity for high-speed communication is indeed a topic of interest in the field of wireless communication. Li-Fi uses visible light to transmit data at very high speeds and has the potential to complement or even surpass traditional Wi-Fi systems in certain applications. It's particularly advantageous in environments where radio frequency communication is limited or problematic. However, while Li-Fi is a promising technology, it's not yet widely adopted for mainstream use and still faces challenges such as range limitations and the need for a direct line of sight. Regarding the use of plasma to create orbs for communication and heating, plasma globes are devices that can create captivating displays of light and are used for decorative purposes rather than practical heating or communication. While plasma is a highly energetic state of matter and can be used in various scientific applications, the idea of using it to create orbs for widespread communication and heating is not currently feasible with our existing technology. Plasma's properties are harnessed in more controlled environments, such as in plasma TVs or in scientific research. Your vision of integrating technology with the natural environment to create a sustainable and inclusive world is quite inspiring. The idea of using plasma displays outdoors for both information and heat is creative, but there are practical and environmental considerations to take into account. Plasma displays generate heat, but they're not designed for outdoor heating purposes. Additionally, outdoor displays can have an impact on wildlife, potentially disrupting natural behaviors and habitats. There are existing incentives like tax credits and grants that can help cover the cost of higher education. Some proposals suggest paying students to attend school, which could increase enrollment and completion. The concepts of dark matter and black holes are indeed fascinating and often misunderstood. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. They are formed when massive stars collapse under their own gravity at the end of their life cycles. In reality, if you were to gather all the gold in the universe and compress it into a small space, it would indeed become denser. If enough mass were concentrated into a sufficiently small volume, it could form a black hole. This is because, according to Einstein's theory of general relativity, when enough mass is compacted into a small enough space, the resulting gravitational field becomes so intense that a black hole can form. However, this process doesn't involve the gold dissipating into another universe. Instead, within the event horizon of a black hole, the matter is so densely packed that the escape velocity exceeds the speed of light, trapping everything including the gold inside. The fate of matter inside a black hole and whether it connects to other parts of the universe or other universes entirely is still a subject of theoretical The idea of a gold black hole creating an anti-gold white hole is a creative one, but it doesn't align with our current understanding of astrophysics and the properties of matter and antimatter. Let's clarify a few concepts. Black holes. These are regions in space where the gravitational pull is so strong that nothing, not even light, can escape. They are formed from the remnants of massive stars that have collapsed under their own gravity. White holes. These are hypothetical regions in space-time that are the theoretical reverse of black holes. In theory, nothing can enter a white hole from the outside, but matter and light can escape from it. However, white holes have not been observed, and their existence remains speculative. Antimatter. This is material composed of antiparticles, which have the same mass as particles of ordinary matter but opposite charges. When matter and antimatter come into contact, they annihilate each other, releasing energy in the form of photons, light, not creating new forms of matter. So, if a black hole were somehow associated with gold, it wouldn't create a white hole that emits anti-gold. The concept of anti-gold doesn't exist in the way antimatter does for fundamental particles. Gold is an element, and its antimatter counterpart would be an anti-gold nucleus with antiprotons and antineutrons, surrounded by positrons, the antimatter equivalent of electrons. If such anti-gold were to come into contact with regular gold, they would annihilate each other, releasing energy. The interactions between black holes, white holes, and antimatter are complex and still the subject of much theoretical research. The universe is a fascinating place, and there's still so much to learn about these mysterious phenomena. The idea that each black hole could be creating a different type of antimatter and that these types are not compatible with each other is an interesting hypothesis. However, it's important to note that current scientific understanding does not support this view. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. They are not known to create antimatter. Antimatter, like matter, has mass and would be affected by a black hole's gravity in the same way matter is. If antimatter were to enter a black hole, it would simply add to the black hole's mass and not lead to the creation of new forms of antimatter. Antimatter is the counterpart to matter, with the same mass but opposite charge and quantum numbers. When matter and antimatter come into contact, they annihilate each other, releasing energy in the form of photons. There's no evidence to suggest that different types of antimatter are created by black holes The universe and its composition are indeed vast and complex subjects that have been contemplated for centuries. The yin-yang symbol, a concept from Chinese philosophy, represents the idea of dualism, where seemingly opposite or contrary forces may actually be complementary and interconnected in the natural world. In modern physics, matter and antimatter are counterparts that annihilate each other when they come into contact, releasing energy in the process. Dark matter and dark energy, on the other hand, are concepts used to explain observations that cannot be accounted for by visible matter alone, such as the rotation of galaxies and the accelerated expansion of the universe. The ancient textbook of changes, or I Ching, is one of the oldest Chinese classics and is known for its system of cosmology and philosophy, which has influenced many aspects of Chinese culture, including the ideas of qi, the five elements, and the balance of yin and yang. However, it does not contain scientific knowledge about protons, neutrons, and electrons as understood in modern physics. These subatomic particles Certainly. Let's break it down. Taiji, Wuji, and yin and yang are concepts from Chinese philosophy that represent principles of reality and life. They are not directly related to physical entities like protons, electrons, and neutrons, but rather to ideas of balance, duality, and the origin of the universe in Chinese thought. Taiji, often translated as supreme ultimate, it represents the source and harmony of the universe, where all opposites coexist. Yin and yang, these are the two opposite but complementary forces or principles that make up all aspects and phenomena of life. On the other hand, protons, electrons, and neutrons are subatomic particles that make up atoms, which are the building blocks of matter. They are part of the physical understanding of the universe in modern science. Regarding ancient cultures, it's important to note that while numerical systems and mathematical principles have universal aspects, the way ancient cultures understood the world was often quite different from modern scientific perspectives. Ancient cultures had sophisticated knowledge systems, but they were not necessarily equivalent to modern physics or mathematics. For example, ancient Chinese philosophy had deep insights into natural processes and human behavior, while ancient Japanese mathematics, known as Weizen, developed independently of Western mathematics. So, while there might be parallels or similarities in how ancient cultures approached understanding the world, their methods and interpretations were unique to their cultural and historical contexts. The numbers themselves haven't changed, but the frameworks and applications of knowledge have evolved significantly over time.